cares? All right. So I will take some time to go through the parameters, INL, DNLs of the ADCs. And we have a quiz today for the voltage doubler, voltage multiplier, and sample and whole circuit, charge pumps. And then we'll give you the quiz on voltage doublers, okay? Go through that really quick, make sure everybody can succeed. So first for this one, we have pretty much 40 to 50% of you guys made it 100%. So it's worth going through this really quick. So for here, since we know that it's a level trigger SR flip-flop, so when clock is on, everything is enabled. Since it gave you a initial state to be 1, okay? So whenever this one enters 0, 0 state, it's a memory. No. Oh, 0, 0 is a memory. So the memory is going to memorize the previous state. Okay, that is why you want to label these two parts, draw a line here, and you want to draw this one, extend this one a little bit to this right hand side, to this edge, and then draw a falling edge because clock is enabled and your R signal is on, so it's resetting your signal. So we're going to look at the clock. So first we're going to look at the clock. Is the clock is on or not? If the clock is on, it is enabled. If it's enabled, it becomes SR flip-flop. If it's an SR flip-flop, you want to look at S and R combinations. If S is 1, it's setting. If S is 0, R is 1, it's resetting. So because this is S is 0, R is 1, this is resetting. Okay, resetting until this point. Then you get into the memory state again, 0, 0. You extend that 0 a little bit further to here. And then you can see clock is still on, still enabled, so which means it's still a SR flip-flop. But now S is 1, R is 0, so it's 1, 0, so you want to set it. Okay? So set it here until this point, and then clock becomes 0, so it's a memory. So memory is going to extend that 1, and you want to, whenever you see a 0 of the clock, it should be really simple since you don't have to worry about anything else. Okay, so you extend that one to this point, then clock becomes 1 again, so it's goes back to the SR flip-flop mode, and we'll look at, okay, clock is 1, R is 1, S is 0, so it's getting reset. So immediately put it down to ground. Okay, put it down to ground. So until this point, okay, R is not 1 anymore. However, both S and R are zeros. It's going to be a memory. So extend that 0 a little bit to this point. Okay, and then your clock is still on, and your S and R becomes 1, 0. So it's going to put up to 1 to this point. And you can see clock is still on, which means it's still enabled. Then R becomes 1, S is 0, so it's resetting it. So you have to put it down to ground and connect your ground signal to this little existing 0 here to make 100%. Okay, if you're missing this little 0 here and this little 1 here, you're probably getting losing like 1 to 2 points. Have to make every single component here perfect. Okay, you're not even perfect. You're asking us to be perfect. Just joking. Any question on this? Any question on this? No? So for today's quiz, it will be really simple circuit from last time. Remember a voltage doubler. You have a voltage source. It's oscillating. Got a capacitor. Got this. Okay, then you have to filter it out. All right. So if this is oscillating like this, and this point is going to lift this voltage up by 50% of the amplitude, and eventually this will be the DC output from that output over here. So look at the notes from Monday's lecture. I'm not going to give you the answer over here, but look at the notes. And I forgot if I asked you to explain that or not, but make sure you understand what's really going on over here. Again, so the main point is after you charge up the cap, and then you trying to add another voltage on one side of the cap, and eventually you got the two voltages added together. If you are looking at this node, the voltage is a lot higher than this one and this one. This applies to the charge pump circuit as well. Okay. Let's have a quick review on this charge pump circuit. We're just repeating whatever we cover on Monday, okay? So if I have this one oscillating, because it's digital signal, so the digital signal doesn't have negative voltages. So this has to be oscillating from 0 to VDD, like this, right? 1 zeros, logic 1, logic zeros. So what is the range of the voltage here at this point? If there's a 0.6 volts voltage drop across the diode, what's going to happen to this point? What is the voltage range? Remember, one key point that I covered on Monday is when you pull voltage down from VDD to ground, when you pull voltage down to ground at the falling edge, it's going to pull current to the cap. That's a key point we taught on Monday. Okay? Something you want to model in your mind. What's that?
Is that another VDD on the left, or is that just a timing diagram?
This one?
Yeah.
0 to VDD, right?
Yeah.
Yeah.
Is it coming in up from the left side as well?
Yeah.
Okay.
Good point. So when this is pulling, keep in mind, when this is pulling, it's going to dump current to the cap and charge it up to VDD. All right? And because this is the diode, so it has nowhere to, the charge will stay and has nowhere to go. And whenever this goes up at the rising edge, it's going to add another VDD to here. And eventually this becomes what? 2 VDD, however, it has to minus 0.6 volts because this diode is forcing that voltage to drop 0.6 volts, right? Similarly, if you have a transistor, here to replace that diode. So when this one pulls voltage from the source, what is the maximum voltage you can see from here at the source of the NMOS transistor? It's a gate drain shorted NMOS transistor. What's the maximum voltage you can see at this point? VDD minus VTHN and Y. What's the voltage at the gate? It's shorted to the drain, and it has to be VDD. It has to be VDD. Okay? So this voltage cannot go higher whenever this is pulling. It's pulling, right? Pulling charges. It's charging up the cap. This voltage will start going up, will start rising. And after it reaches this voltage, it cannot go up anymore because whenever it's a little bit higher, the NMOS will be shut off. The reason for that is VGS equals VDD minus VTHN, which is VDD minus VDD plus VTHN. And this is cancelled. So your VGS becomes VTHN. All right? If it's going higher, your VGS will be less than VTHN. It's going to shut off this NMOS. So this will be the maximum voltage you can see at the source. So which means whenever this is pulling, the maximum voltage can reach the source of the NMOS will be VDD minus VTHN. Or you can say whenever the VDD is passing this NMOS transistor, it is losing 1 VTHN. I'm telling you that I can have my VDD higher, for example, like this. I'll let you see that circuit later, but now I'm adding a 2 VDD to the gate and 1 VDD to the drain. What is the maximum voltage you can see at the source? Are you still losing VTHN or no? Are you still losing anything? Are you able to pass the entire VDD to the source? Yes, right? Why is that?
Because 2 VDD minus VDD will still be greater than VTHN.
Correct. So now VGS is VDD minus, 2 VDD minus VDD, which is 1 VDD, which is still way larger than VTHN. Okay? So in order to pass the entire VDD to the other side, what you want to do? You want to increase your gate voltage. Okay? But when you are having your power rail being applied to all the transistors, and most of the time the highest voltage available in the circuit will be VDD, and you are pulling your N wells to VDD. So it's been the highest voltage available. Okay, so I have to use a special circuit to boost the gate voltage of that transistor, which requires a higher voltage to pass the entire VDD to the source. So that is why we need a charge pump, because the charge pump is able to pump it up to a value which is larger than 1 VDD, like this. So for here, it becomes 2 VDD minus VTHN and VDD minus VTHN. Okay, it's going to oscillate between these two voltage nodes. Eventually, the output here, okay, it's going to look like this. It's oscillating above your VTHN. Okay, so it's going to oscillate from VDD minus VTHN and 2 VDD minus VTHN. Make sense? Okay, now let's see how we can do it for the circuit that we need to use for the sample and hold circuit. Any question on this? Does everyone get a concept that when it's pulling, it's dumping charges to the cap and charging up to VDD minus VTHN? Whenever it's getting flipped to VDD, it's adding a VDD to that VDD minus VTHN, so it becomes 2 VDD minus VTHN. Right? Any question on this? Is that clear for everyone? So when I want to stabilize this voltage, I can add a transistor, like a diode transistor and a cap. So this part of the circuit is very similar to this one we introduced on Monday, right? It's just a filter. Oh, one more question for you guys. It could be on the quiz. Why this is called diode connected? Oh, sorry. Why is this the diode? Why is this the diode? NMOS transistor has a gate drain connection and becomes a diode. Why is that?
There's just one junction.
Just one junction. So this one is still a gate, right? So it has two diffusion. It's definitely physically it's not a diode, but it performs as a diode. So for the NMOS, it's this. Okay. How do you make a diode? We haven't done that yet, right? So there will be a chance to lay out the diode for the ESC protection for the pads. So physically, how do you lay out the diode? I'm not trying to distract you, but it's just something I don't want to forget to cover. So for example, in your electrical VLSI, how do you lay out the diode? So basically, if you think about the PMOS, the P-N junction, it's a P sub, right? It's a P sub. So in order to make a diode, you need a P-N junction. So first of all, you need a, let me see. Let's see if this works, okay? P plus, for example, and N plus, or N well. I think it has to be N plus, N plus. Because we short the P sub to ground to the lowest potential of the circuit, right? Everything's in the same P sub. You can separate the N well, but you cannot separate the P sub. Do you understand what I'm saying here? Can you put PMOSes in different N wells? It works. Doesn't matter. Can get a PMOS here. It works. Can you place NMOSes in different P subs? Can you put NMOSes in different P subs? Break it. Just kidding. So you cannot. Okay, they have to be in the same well. All right. So now let's look at this one. So for the top view, if you're doing a layout in electro VSI from the top, so if you make an N material like this, N plus, okay, and place the P. Wait, let me see. No, this should be N well. These are contacts, but the whole thing should be N well. Okay, N plus. And you place a little P plus in here, and let's see if that works. Okay, so this forms a diode. Okay, it's from the diode. And if we connect this one to 5 volts, this to ground, did you see any problems? I'm using this one as a diode. Okay. Do you see any problems here? I think it's gonna work, okay? So it's gonna flow current this way and go back to here. So this one doesn't have to be ground. You can connect to any other circuits over here. And this N plus is separating the P plus from P sub because your P sub is grounded. You don't want to directly place your P plus in P sub. It's gonna short your P to ground. Okay, and because your P sub is the lowest potential in the circuit, so eventually there won't be any forward biased diode being formed over here. There won't be any undesired ones being formed over here because your P sub is always grounded. So it's always reverse biased. So you'll be fine. Okay, you'll be fine. So when you are doing the layout, what you can do is, I'm going to redraw it, okay? You draw a N plus material, and you place the P plus material in the middle. Okay? And have a little contact everywhere because it's a pretty long, have a bigger footprint. And you can introduce drill via here and connect it to metal one for these two pieces. Okay, so it becomes a diode over here. All right, so you can see these are different, right? These are different. For the layout, the cross-sectional view, so the P-N junction looks like this. It's a very simple diode. And the NMOS is still NMOS, right? It has P plus and all the channels. So the point here is, if you connect your transistor this way, it performs as a diode. And the reason for that is the current is not going backwards, similar to the diode. It's not going backwards. So my question for you guys is, why is that? Why the current is not going backwards? Since when we are doing the layout, we can tell that basically source and drain are equivalent. There's no significant difference between these two nodes. They are just basically N plus materials, right? For the C5 technology, it's really simple. They made it the same. When you are doing the layout, you can tell they are exactly the same diffusion on the two sides. So in that case, why this one is able to pass current from top to bottom, but not bottom to top? Yeah, I talked about this very briefly on Monday, but I don't expect that you guys can remember. So why the current is not going up? Why the current is not going up? It's really simple, right? It's really simple because of VGS is 0, right? GNS is shorted, so VGS is 0. There's no, if you treat this one as a drain, you won't be able to flow current that way because VGS is 0. So VGS has to be larger than VTH in order to flow current, but now it's 0, so it's only flowing current in one direction because this VGS here is not 0. It's larger than VTHN, so you are able to pass current that way. Okay, similar to the diode. You're only able to pass current from top to bottom, but not bottom to top. Okay, so we can use transistors because it's more a standard way to build highly integrated circuits. So we prefer to use these transistors to build the charge pumps like this. And you can have more stages adding to this structure and forming the Dixon's charge pump. Okay, eventually you can look at your notes from Monday, what that charge pump looks like. Okay, so now we can, after we can understand this how the charge pump works, we can run a quick simulation first before we get into the sample whole circuit. Let's see. I have a 18_34, which is the circuit from the textbook. Okay. All right. So this input pulse is being inverted. It doesn't matter. It's just a pulse, right? It's being inverted, still a pulse. Just have a phase shift on that. So this is a little capacitor, and that's a diode connected NMOS transistor, and that's the filter. That's a filter. And if I run it, oscillation, no problem. And this one will be lifted. Will be lifted, but still oscillating. So it's oscillating between. Also, the VDD here is 1 volt because I'm using a model file from the textbook. It's a fake model file. You cannot use it to fabricate for anything. It's a 50 nanometer technology, which has a VDD to be 1 volt. It's used for building all these low power circuits. Okay, but it's a fake one, just for simulation purposes from the textbook. All right, so this one you can see it's definitely being lifted to VDD minus VTHN, right? So this is 2 VDD minus VTHN. This is 1 VDD minus VTHN. And eventually VL is being filtered and becomes a DC voltage. So the VDD is a power supply. Okay, keep in mind, power supply. So power supply is only 1 volt, but eventually you are generating a 1.4 volts DC voltage in the circuit. Okay, so that voltage will be higher than the voltage connected to the N wells because N wells are shorted to VDD. Keep that in mind. Why that is important? So this should be some sort of like alert when you are thinking about circuit. Anything becomes higher than the N well, or pay attention to it. A large-scale integrated circuit has a lot of PMOSs and NMOSs, and PMOSs are building N wells. Okay. So the material, what is the material of the N well tap? When you have these things, You are shorting gates to each other, right? To form an inverter, like this. Okay. So these are unwell taps. And unwell taps should be in the same unwell as your PMOS. So eventually, as a standard way, you should draw a pure unwell material to cover the PMOS and unwell taps. And if you draw a cross-sectional view, it looks like this because your unwell tap, which is N+ material, should be in the same unwell as your PMOS. And you are shorting your unwell to VDD to avoid what? Body effect. Where's the body effect? So the PMOS, you are adding a relatively negative voltage to your gate, so it's attracting holes to it, right? It's attracting holes to it. So the body effect means whenever this one is, you have a forward biased diode, and eventually it's stealing your holes from the gate, and eventually increase your threshold voltage. Okay, so because N+ is unwell, because they are same material, they are shorted to ground to VDD. So basically, you are shorting your cathode to VDD, so you can keep your diode always reverse biased, so it's not getting forward biased. Okay, you don't want this undesired diode to be forward biased. That is why you are shorting this one to VDD, right? So in that case, you want this unwell, which hosts the PMOSes and N-tap in the same unwell. So that's why we want to draw a pure unwell material to cover both the N-taps and the PMOS. Any question on this? So this becomes very important because whenever we have higher voltages, this is required. Sometimes you have to separate your unwell with the higher voltage from the unwell with the lower voltages, which is VDD. Let me show you this really quick. Several questions. Will be a quiz on Friday. Okay. This is from 0 to VDD. Let's look at this circuit. A few things we need to know. Ratio 20 to 1. Ratio 100 to 1. Here 100 farads. Femtofarads. 1000 femtofarads. Femto is what? Femto is 10 to the what? -15th, right? Okay. And this one is a big inverter used as the buffer.
Why are those inverters, why do we use the symbol for the inverter there and not the MOSFET version there?
Good question. Because this, you mean this one, right? Yeah, because this is a special inverter. Did you see these inverters? Do I connect to the VDD and ground, even though I don't have it? I do, right? Remember in the schematic you have to. So actually they have power rails, right? You'll see this one has a different power. This is short to VDD, right? So the power is not VDD, it's over here. Very good question, okay? Notice the difference. So it's gonna ask you what is the output, what the output looks like. I didn't label VDD and ground for these inverters, so you should know that by default, this should be shorted to VDD and ground, right? By default. Okay, what's happening to this guy? VDD and zero oscillation is gonna pull. We have to start with something, okay? Let's start pulling. Let's start pulling. If this is pulling, what's happening here? It is pulling, then this one, VDD will charge up the cap. It's gonna charge up the cap, okay? And give you a VDD minus VTHN here. Okay? When this is pushing, doesn't matter, don't worry about the inverter, it's just VDD and ground oscillation here, okay? So when this is pushing, it's adding another VDD to it. So it's 2 VDD minus VTHN. Alright? And this voltage over here, is shorted to the gate of the other NMOS. So which enables this one to pass because these voltages are larger than, at least this one, right? This one. So the reason for that is you can see this signal is getting inverted. This signal is getting inverted. So whenever this is pushing, I'm going to repeat this one more time later. Okay, don't worry about that. So whenever this is pushing, the voltage across the capacitor becomes the larger one of it, the larger one, okay, not the smaller one. It's going to be the larger one. With pushing, keep in mind, with pushing, it's adding one more VDD to it, okay. So whenever this is pushing, because it's getting inverted, so the signal right here is pulling. You know what I mean? What's that?
Is the clock connected to the leftmost inverter? So that's going VDD to 2 VDD?
No, it's just VDD and ground.
Oh, it's just grounded?
Yeah,
Okay.
VDD and ground. All right, here comes the key point. Let's see if you guys can get this point, okay? So whenever this is pushing, trying to push a VDD to it, okay? So this becomes what? 2 VDD minus VTHN, okay? So because this, you are adding an inverter to this line, so whenever this line is pushing, the line here is doing what? It's pulling. Because these are inverted. So whenever this is pushing, like rising edge to VDD, and this is a falling edge from VDD to ground. You agree with that? So whenever this is pushing, it becomes a higher voltage. The higher one of it, of the two. The higher one of the two. And this is pulling. So when this is pulling, it's doing what? It's charging up the cap from the VDD. It's dumping charges from VDD to this cap. That makes a lot of sense because whenever this is being pushed to the higher voltage and shorted to the gate, you are getting a higher voltage at the gate, and which will be able to widely open this NMOS, just open it wider, and which is able to pass the entire VDD to the cap because this guy is pulling. One of the most important point we have been trying to cover in the recent 2 weeks. Okay, so whenever this is pushing, it's adding 1 VDD to this value, so we are getting a higher voltage, the higher one of the 2 voltages available, right? So it's oscillating between these 2 voltages and becomes a higher one. And this higher one is larger than VDD, we can tell, and this one is smaller than VDD because the minus is subtracting the VTHN from the VDD, okay? But this one is definitely larger than VDD, okay? If this is larger than VDD, like we said from the previous page, if I'm adding a 2 VDD here, am I able to pass the entire VDD to this point? Of course, because the gate voltage is bigger than VDD. So whenever this is pushing, this is pulling. This pulling is trying to dump the whole charges of the VDD to this cap. Eventually, it's able to pass the entire VDD to this cap because the gate voltage is higher than VDD. Any questions on this?
So if the first one pulls, it's VDD minus VTation, but the second
Yeah.
one when it pulls,
It's gonna push.
it's VDD.
Yeah, so if this is pulling, right? It's pulling. It's pulling this voltage from VDD to this point, right? What's gonna happen to this one? It previously stores the 2 VDD here, so eventually it's gonna shut this off because this one is less than the source voltage. Let me label the voltage here. So this one is gonna oscillate from VDD 2 VDD minus VTation. 2 VDD minus VTation. It's probably not even minus VTation eventually. But now let's just assume it's a minus VTation for now. It's just the first cycle, okay? Just the first cycle, it's okay? Eventually, it will be able to get rid of the VTations. But now just the first cycle, it's not ready yet. So for this one, whenever this is getting a VDD minus VTation over here, and this one is pushing, because this is pulling, this is pushing, okay? If this is pushing, it's getting 2 VDD minus VTation, and you are getting a VGS less than 0. So it's shut off. So it's not going, so the charge is not going to anywhere. It's disconnected. So the charge will be stored across the cap. Okay? And because it's able to pass the entire VDD here, and eventually it's not losing the VTH anymore. Okay? So it becomes VDD to VDD after the first cycle. Sarah's like, I'm not interested in this. Teach us something else. I'm kidding. All right. So, eventually, this becomes the voltage here, right? So my question is, what about the oscillations over here, though? Because it seems like the VDD point of the PMOS, right? It's oscillating between these two voltages, VDD and 2 VDD. What about this one? It's just VDD to 0, right? And what about the output? It is just a regular inverter. If the input of the inverter is 0, what is the output? I have to look at the phase, right? The phase. So, for example, just look at this point. If I'm getting a VDD, one VDD, it's inverted. So VDD here means 0 here is pulling. This is pulling, you're getting VDD. What is the voltage here? Let's do this one more time. If this point is VDD, just digital signals is way easier than analog, okay? We shouldn't complain, it's so easy compared to analog. So if this point is VDD, one VDD, what is the voltage here? Yeah, 0. Good. If this is 0, what is this doing here? What is this cap doing? Pulling or pushing? Pulling. Okay? If it's pulling, what is the voltage here? VDD. It's pulling VDD to this cap. So if it's VDD, what is the voltage here? Still VDD. Okay? If this is a VDD, which is on? Which one is on? Is the PMOS on or off? You can even answer this during the first week of the semester. You just got fried. Your brain's fried. If this is VDD, okay, it's a 1. 1 is going to shut off the PMOS, so there's nothing going to put up to VDD, since we know this is VDD, okay? So if VDD, here's 1, this NMOS is on, so this point is being put down to ground. So what is the voltage here? This is on, what is the voltage here? If this point is put down to ground, what is the voltage here? Yes, okay. This is 0, okay? So VDD, you got a 0, okay? That's one of the options. You can only got 2 different inputs. If this is VDD, you got a 0, okay? If this is 0, what is the voltage here? VDD, okay? If this is VDD, is pulling or pushing? Pushing. So what's the voltage here across it? 2 VDD. If this is 2 VDD, what's the voltage here? Still 2 VDD, okay? So whenever the input of the inverter is 0, which one is on? PMOS is on, right? PMOS is on, NMOS is off. If this is 0, NMOS is off, PMOS is on. PMOS is on, it's pulling this output pin up to the source of the PMOS. So what's the voltage at the source of the PMOS? 2 VDD. So what's the voltage here? 2 VDD, right? So eventually the output is going to oscillate from where to where? Yep. Now let's look at the PMOS. Compared to other PMOSes, it's imposter. It's different. How do we deal with it? Why is different? You're like, hey, Dr. Lee, we don't have other PMOSes. Do we have other PMOSes? Do we have other PMOSes? Yes. Here, we have PMOSes here and here. Yeah, even though these are NMOSes, we have PMOSes anywhere else as well. So it's in all the places on the chip. So this PMOS is different because the source of the PMOS is 2 VDD instead of 1 VDD compared to other PMOSes. And why that is important to know. Why is that? So from the cross-sectional view, you have P plus, and here's the N plus, and this is your N well. Remember, for the PMOSes, is just think about the electric VI side layouts, right? So what's the signal line here? VDD, right? So these are the N taps, this is the N plus. These are P plus, PMOSes. And that's the N plus. N plus shorted to the N well. It's called the N tap. So we want to short the N tap or the N well to the highest potential of the circuit to avoid body effect, to avoid forward biasing of the diodes. Okay, look at this one. Here's a little imposter here. Every PMOS has a little N plus. Let's just draw N plus over here. Sorry about that. And all these are shorted to VDD. Okay, so if this N plus of the regular PMOSes are shorted to VDD, which means this N well is shorted to VDD. You agree with that? Because N plus is shorted to N well. These are same materials, they are shorted. So if N plus is shorted to VDD, your N well is shorted to VDD. However, for this little imposter, the source of this PMOS is shorted to where? Sometimes it goes to 2 VDD. What's happening? What's happening? Can you see it? PN junction, and the P is 2 VDD and N is VDD. Something goes wrong. It's going to flow current to this undesired diode. So how to avoid this?
Separate the NMOS. Separate envelope?
Separate NMOS. These are all PMOSes.
Separate and well.
Separate and well, yes. How to separate it? Crack it. No, just have a separate and well, right? You don't have to crack the wafer. Has its own tap, N-tap. So this N-tap should be, N+ should be shorted to where? 2 VDD. You guys are like, oh, I need another power supply. Let's increase the cost. Where?
What was the question?
So where should I short this N-tap to or N-well? So the one with the higher voltage. So these are regular ones, right? VDD, no problem. So what about the one with the higher voltage, like this PMOS? Where should I short the body? So the body of the PMOS, which is N-well, right? So the body of, you guys are like, when should we do the quiz? Let's do it on Friday. So where? You're always thinking about the quiz, not following. Where should I short this N-well to? N-well. N-well is the PMOS. N-well is the body of the PMOS, right? N-well is the body of the PMOS. Now this one, we know that these sources are sometimes getting to like 2 VDDs. It's a problem. So where should I short this N+ to make it to avoid any forward biasing undesired PN junctions?
2 VDD?
But where's 2 VD?
There, on top of the capacitor.
Here, right? And what is that? Where is it? It's just the source of the PMOS. Okay? They are equal. Any forward biasing? Impossible, right? So what should we do for the schematic? In your electric VLSI, most of the devices don't have the force terminal, right? I mean, during the first lab, I think you learn how to introduce the force terminal, which is the body of the transistor. But after that, we all assume that the body of the PMOSes are shorted to the same node, which is VDD, and the body of the NMOS is shorted to the same node as well, which is the ground, right? So that's why we just ignored the force terminal. But for this one, if you ignore the force terminal, by default, the body of this transistor in schematic will be shorted to VDD, shorted to the regular NMOS PMOS's body. And eventually, you separate it in your layout. You can definitely manually do it, right? You know how to do that, right? In your N-well, just don't have that shaded area overlap. Just separate them. The dotted area of the PMOSes, just don't let them contact, okay? And when you are drawing like these ones, where is it? Okay, here. You eventually draw a universal N-well to cover both the N-taps and PMOSes, but now you just don't do it. You have another PMOS next to it, have them separated, so you don't have the universal N-well to cover both. Okay. However, in your schematic, you have this. You don't have the force terminal, and eventually, it's not going to pass well check. We haven't done a well check yet. I don't know if it's going to pass NCC or LVS, but definitely schematic and layout don't match. You know, because this one doesn't have the force terminal, so by default, the force terminal is shorted to VDD. However, here, you short it to the source, but not VDD. You know what I mean? So in that case, you need to grab a 4-terminal PMOS device and short it here manually. Okay? You do this in schematic, and you do the same in your layout like this, and separate the N-well. So they will pass LVS, they'll pass well check. Make sense? Okay, there will be 2 quizzes on Friday. No, probably just one. Just one. Another one will be on Monday.
Which one?
Which one? The multiplier one on Friday. Monday will be this one. So study this guy, okay? There will be a few points. For example, the voltage here, voltage here, voltage here, voltage here, voltage here, the well check, and all these kind of things. Okay, study this note. Okay. Yeah, turn it back to me. Give it back to me. The quiz from last time, so I can lock the grades canvas.